Look around you. Everything you see, from the smallest grain of sand to the most distant star, is made of matter. But why is there something rather than nothing? And why is there more matter than antimatter? These are some of the most fundamental questions in physics, and they lead us to the mystery of baryon asymmetry. In the simplest terms, baryon asymmetry refers to the imbalance between matter and antimatter in the universe. It's the reason why we exist at all. To understand this imbalance, we need to rewind the clock to the very beginning, to the Big Bang. The Big Bang theory tells us that the universe began as an incredibly hot, dense state. In the first fractions of a second, the universe was a seething cauldron of particles and antiparticles constantly colliding and annihilating each other. Particles and antiparticles are like mirror images of each other, with the same mass but opposite charges. When they meet, they annihilate in a burst of energy. If matter and antimatter were created in equal amounts as expected, they should have completely annihilated each other, leaving behind nothing but a sea of radiation. Yet here we are, in a universe dominated by matter. This means that somewhere along the way, a tiny imbalance must have tipped the scales in favor of matter. This excess of matter, though small, was enough to seed the formation of stars, galaxies, and eventually life itself. This imbalance, this baryon asymmetry, is one of the most puzzling mysteries in cosmology. It suggests that the laws of physics might not be perfectly symmetrical between matter and antimatter. In 1967, Russian physicist Andrei Sakharov proposed 3 conditions that must be met for baryon asymmetry to arise in the early universe. This groundbreaking idea was a significant step in our understanding of why the universe is composed predominantly of matter rather than antimatter. These conditions, known as Sakharov's conditions, provide a framework for understanding how this imbalance might have occurred. They are essential for explaining the observed dominance of matter over antimatter in the cosmos. The first condition is that baryon number, a fundamental quantity that distinguishes matter from antimatter, must be violated. In simpler terms, there must be processes that can change the number of baryons, which are the particles that make up the nucleus of atoms. This means that processes must exist that can create or destroy baryons, the building blocks of matter. Without such processes, the universe would have equal amounts of matter and antimatter, leading to their mutual annihilation and leaving behind a universe filled with only radiation. The second condition requires that the symmetries of charge conjugation, C, and charge parity, CP, be violated. Charge conjugation symmetry suggests that the laws of physics should remain unchanged if particles are replaced with their corresponding antiparticles. Charge parity symmetry, on the other hand, implies that the laws of physics should be the same if we swap particles with their mirror images and antiparticles. However, for baryon asymmetry to occur, these symmetries must be broken. Violation of these symmetries implies that matter and antimatter might behave slightly differently. This difference in behavior is crucial because it allows for a small excess of matter over antimatter, which is necessary for the existence of the universe as we know it. The third and final condition is that these processes must occur out of thermal equilibrium. In the early universe, conditions were extremely hot and dense, and particles were in a state of thermal equilibrium. However, as the universe expanded and cooled, it moved out of this equilibrium state. This departure from thermal equilibrium is essential because it allows the asymmetry to be frozen in as the universe cools. Without this condition, any created asymmetry would be washed out by ongoing interactions that would drive the system back to equilibrium. Today, scientists continue to study these conditions using advanced particle accelerators and detectors. By recreating the high-energy conditions of the early universe, they hope to observe the processes that led to baryon asymmetry, and gain deeper insights into the fundamental laws of nature. Sakharov's conditions remain a cornerstone of modern cosmology and particle physics. They provide a vital link between the microcosm of particle interactions and the macrocosm of the universe's evolution, helping us to understand the very fabric of our existence. As we continue to explore the mysteries of the universe, the work of Andrei Sakharov serves as a reminder of the profound connections between the smallest particles and the vast expanse of the cosmos. His legacy lives on in the ongoing quest to unravel the secrets of our universe. The third and final condition is that the universe must have been out of thermal equilibrium. This is crucial because, in a state of thermal equilibrium, the universe would have been too balanced to allow for the creation of more matter than antimatter. Thermal equilibrium is a state of balance where energy is evenly distributed. In such a state, any process that creates a matter-antimatter asymmetry would be counteracted by another process that destroys it, maintaining a perfect balance. If the universe were in thermal equilibrium, any processes that created a matter-antimatter asymmetry would be balanced by processes that destroyed it. This means that the universe would remain in a state of symmetry, with no excess of matter over antimatter. While we have observed CP violation in particle physics experiments, the amount of CP violation we see is not enough to explain the observed baryon asymmetry. CP violation refers to the differences in the behavior of particles and their antiparticles, which could potentially lead to an imbalance. This suggests that there are still missing pieces to the puzzle, and new physics beyond the standard model of particle physics might be needed to fully explain this asymmetry. Scientists are actively researching and developing new theories that could provide the answers we seek. These theories might involve new particles, forces, or interactions that have yet to be discovered. The quest to understand CP violation and the matter-antimatter asymmetry is ongoing, and each new discovery brings us one step closer to unraveling the mysteries of our universe. Despite the challenges, we have made significant progress in understanding baryon asymmetry. Observations of the cosmic microwave background radiation, the faint afterglow of the Big Bang, provide strong evidence for a matter-dominated universe. The abundance of light elements like hydrogen and helium also supports the Big Bang theory and the existence of baryon asymmetry. These elements were created in the first few minutes after the Big Bang, and their observed abundances agree remarkably well with theoretical predictions based on a matter-dominated universe. The mystery of baryon asymmetry is far from solved, and it continues to drive research in cosmology, particle physics, and astrophysics. Scientists are exploring various theoretical models and conducting experiments to search for new particles and forces that could have played a role in generating this asymmetry. This quest is not just about understanding the past, but also about predicting the future of our universe. The quest to understand baryon asymmetry is a journey to unravel the fundamental nature of the universe and our place within it. It involves peering back in time to the moments just after the Big Bang, where the seeds of this asymmetry were sown. It is a journey driven by our insatiable curiosity to comprehend the cosmos and the laws that govern it, and it requires the collaboration of brilliant minds from around the globe. Pushing the boundaries of knowledge and challenging our understanding of the universe we call home. Each discovery, no matter how small, brings us one step closer to answering some of the most profound questions ever asked. What caused the imbalance between matter and antimatter? How did this asymmetry shape the universe we see today? These questions drive the relentless pursuit of knowledge, inspiring new generations of scientists to delve into the mysteries of the cosmos. The journey is arduous, filled with challenges and setbacks, but the potential rewards are immense. Understanding baryon asymmetry could unlock new realms of physics, offering insights into the very fabric of reality itself. As we continue this quest, we are reminded that science is a never-ending journey, a continuous quest for answers that propels humanity forward. The quest for baryon asymmetry is a testament to our enduring spirit of exploration and our unyielding desire to understand the universe in all its complexity.